Hello, welcome to our today's online seminar about elemental analysis of liquids and sludges by XRF. So we are covering topics from galvanic coating to mine tailings or catalyst recoveries. And my name is Kai Behrens, and today with me is Adrian Fiegel.
Yeah, hello, and also very warm welcome from my side to today's online webinar.
So we will quickly cover ideas about process and quality control of liquids, give you some ideas how to deal with slurries and show some application examples. Then we will go on to a lab session with Renata and move on, focusing a little bit more on environmental applications and give you some ideas how to prepare their inhomogeneous samples, and show you in the lab session number 2 the new SA Tiger Series 3. And last but not least, we will go into a Q&A session with our experts at the end. Okay, so just to give you a brief idea, means XRF is seen as a very perfect method for industrial quality control or process control. The advantages are pretty clear. It's the fast, simple sample preparation, simply mechanically, and we achieve with a very good sample preparation and paralleled accuracy and precision. So whenever we have calibration samples, the routine samples and preparation matches each other, we are achieving very high accuracy here. And okay, sometimes we are running into problems like residues in tanks, or we find some sticky stuff here. We have ashes or garbage or waste, or we are seeing slurries as intermediates in a process. And then sometimes people think XRF can be pretty difficult, and we will give you some ideas how to move on here and to get good results anyhow of any sample appearance.
Okay, great.
Yeah, it means one of the big advantages of XRF is that we are actually doing analytical science independent of chemical boundings. And the reason is quite simple. We are using inner electrons, despite other methods like optical emission or things like that. So therefore, we can work with XRF with solid samples. So we are hitting the sample atom actually with an X-ray beam of the responsive energy, and then we are expelling an inner electron. And what happens now actually that from an outer shell an electron falls down and releases the excess energy as an X-ray photon, which is very particular characteristic for the element itself. And there are just a few lines, so XRF spectra are not so complex. And now we simply can see and analyze by the energy, we can see the element, and by the amount of photons actually we know about the concentration finally. Here you see also a link in YouTube, the Bruker YouTube channel, where you get more detailed explanation. So we basically have two instruments, energy dispersive XRF, which actually exciting the sample with a lower power X-ray tube, and then we see with one single semiconductor detector, we see all the X-ray fluorescence radiation at once. And the detector is a pretty cool electronic device because it can, on the one hand, separate the different energies and actually record the intensity for each energy. And so it's a very simple setup, a simple operation, and it's often used in monitoring or whenever requirements are not so critical. Here you also see the more, let's say, kind of advanced setup. So we have an X-ray tube again. It's more a high power X-ray tube going from 401 kilowatt up to 4 kilowatt in total. And after exciting the elements in the sample, actually we are entering the goniometer seen here, consisting actually of a collimator, a crystal changer, a scintillation counter, and a flow counter for light elements. So what happens here actually, we form a parallel beam in the collimator. go to a crystal, and actually this crystal works similar like a prisma we know from optics, actually, and there it separates the wavelength and reflects it to a different angle. And what happens is then we are going with a simple detector, a scintillation counter for the medium and heavy elements and a flow counter for the light elements, and detect the energies, energy by energy or element by element. The big advantage is we are collecting more photons, which end up in a better counting statistics. So we have typically lower LIDs or better analytical precision. And because of using in crystal, actually we are achieving higher resolution.
Yes, exactly. And the difference can also be seen here in this plot, right, Kai?
Exactly. So when you look at the yellow curve, actually you see an energy dispersive spectrum, and what you would recognize, there is a decent manganese peak, a decent iron peak. And when you look at the black curve, actually you see the wavelength dispersive spectrum. And there you suddenly see that there are also some K-beta peaks. And this is quite impressive to see, and this gives you an idea. When you have a simple application, a few elements, energy dispersive is a very good technology. But as soon as you're moving into more complex samples and you want to have very good accuracy, actually, then you don't like to do overlay corrections by estimating the overlay. You want to have physical separation, and this is done by wavelength dispersive. So in this case, actually, when looking, for example, for rare earth elements, then you would prefer to go to wavelength dispersive XRF because of the better resolution. Or if you are looking to go to cobalt or very lower concentration of chromium here, just to get rid of all the overlays.
Exactly. Well, Kai, thanks for the technical introduction. Now let's talk a little bit about samples. Like you said, today's webinar is about a little bit more complex samples, heterogeneous samples, so to speak. Can be crude oil, sludges, maybe soils, anything that's coming maybe from recycling, environmental. However, in any case, there are always the same types ways to present a sample to an X-ray device, and this is depicted here on this slide. So you can put a material into a liquid cup. It's called liquid cup, but it can also be a powder or some slurry or so. You can have a powder that you grind and press into a pellet, or you can take the entire material, ignite it with a flux, essentially, and turn it into a glass bead with a very light matrix. So these are the three options. There are always pros and cons about this. As you can imagine, if you start with a material that you put as is into a cup with a thin polymer foil at the bottom, it's the fastest method. But especially if it's a heterogeneous sample, it can be quite challenging to get, let's say, representative data, repeatable data, and also the foil will absorb some of the intensity, especially from the light elements. When you dry something, grind something, press it into a pellet, well, first of all, because of the drying and grinding, you have a more homogeneous sample, which is better to represent to the system. It's well distributed, so you don't have so much challenge with different intensities from different depths of within the material. And you have also no foil in between, so better sensitivity for lighter elements. And then last but not least, in those powders, you still can have mineral phases. And these mineral phases and grain sizes, they can have some, let's call it, negative effects on your spectra. So they can contaminate your spectra to some extent, and therefore having some impact on especially the precision and accuracy of your measurements. And this is what you can overcome with fusion. In the fusion with a fusion, you typically dilute by a factor of something like 1 to 8 or so, 2 to 8, so 2 grams of material, 8 grams of a flux. So you have some dilution. You destroy essentially all the matrix effect. So you can have also very broad calibration for a wide range of materials. And that means for the major and also the minor concentrations, so at a percentage level or maybe slightly sub-percentage level in weight percent, you get very precise and accurate results. And you can also have global calibrations. Of course, a bit more effort involved here.
Yeah. Means actually, this is also looking a little bit like investment in time pays back in precision and accuracy. So loose powder grains just pour into a cup is pretty quick. Doing a pressed powder with a little bit of grinding and pressing is medium. And actually, if you go then a step further and do the fusion, you invest a little bit more time but you get better data quality.
And at the end of the day, it always depends on your application requirements. What are the needs? What accuracy you need? And this is where we can also provide the guidance for your application. What is the best to choose? That all results together, what Kai explained in the beginning and what I now explained a little bit about sample preparation, that there are some significant advantages versus methods like ICP-OES, where we have to digest the sample and dilute the sample before we can analyze it. So XRF overall allows you to measure the sample quite quickly after sampling. So a little bit of sample preparation on the matter of a few minutes, and then you can analyze it. The systems are also incredibly stable, so they can be operated essentially 24/7. So you don't need to calibrate the instrument daily and have a startup time before you even measure this first sample. So this means when you have when you're receiving in the morning samples and your client wants to have a response within a couple of hours, you can do it with XRF, whereas with ICP, you would have the typical delay. It's also quite easy, we'll show this a little bit, to operate the spectrometer. So it can be done by shift workers, typically, after the system is set up on the method side. So you don't need high-trained lab technologists, lab technicians, and you don't need hazardous or expensive consumables. So these are all things that help you to have a low cost of ownership and high throughput in a production environment, for example. We talked a bit about the preparation, and like today is about more heterogeneous samples. And this is a little bit depicted here again. Some things I already mentioned, but just to show you again, here this is like an illustration, a sketch of a pressed pellet where you see grains of some materials and grains of other materials. As you can imagine, as coarser this is, as more likely it is that you don't get a representative signal from the sample. There's also just a certain information depth. So the X-rays penetrate into the sample and only certain X-rays make it back out of the sample into the detecting part of the instrument. And this depends also on the energy of wavelength of the emitted photons. So for example, signals that come from lighter elements within the sample, only the information comes from a first very thin layer of a few microns. When you have heavier ones, it penetrates back into a few millimeters and even centimeters where you get information. And this makes it, especially for light elements, and this also includes things like silicon, aluminum, magnesium, quite important that you have a homogeneous presentation and also an even surface.
Yeah, means one of the things which can be easily explained looking at the two drawings actually is that for coarser samples you would require sample rotation. And therefore, typically this is whenever you are having pressed powders, loose powders, sample rotation helps because actually the sample rotation helps a little bit to have a representative presentation of the sample to the instrument.
Exactly, and the same is for a good spot size, that if you get more information from the sample. But now how about loading a sample that is more liquid easily in a cup? That is shown on this slide. So you can pipette or spoon it into a liquid cup as shown in the central picture here. Typically you use something like 5 to 10 grams of sample. You don't need any dilution. You might need some stirring and mixing. We'll come to that a little bit later. And then you simply can load the sample into the device. There are different classes of devices, like this is one from a very small benchtop device here, where you would load it manually. But then there are also large floor standing devices with many positions where you can load your sample into an auto changer. That will be shown later by Renata. But what happens if a liquid sample breaks? Is the system protected? How do we ensure that the system can truly run 24/7 in a tough environment, in a dusty environment? And our answer at Bruker to this is sample care. So we have a multi-layer sample care technology in all our XRF devices, which ensures the protection of our vital system components, which are in an energy dispersive system as shown here, the tube and the detector mainly. In the wavelength dispersive system, also the goniometer, which Kai has shown before, which has quite sophisticated technology inside. Shown here, this is from the S2 Puma. We see that we protect the tube, we protect the detector if a leakage happens from a sample, and if the leakage happens, the material is coming here into a reservoir, which can be cleaned by yourself. So if a sample breaks, it's not the end of the world. You simply clean it yourself. There's also something called liquid cup detection. So the system would detect the sample and ensure that it's not run, for example, with the wrong method, such as under vacuum. In some cases, you might want to add an extra level of security, and that's shown on Kai's side here with the images. That's what we call cup-in-cup technology. You can even add another layer of cups because we have a large spot size, we have a relatively large chamber where you can reach in. We are having this technology to use a double cup technology with two foils. Mm-hmm. Okay, and with that, we are essentially done with the first part. And right when we talk about sample preparation and sample handling, I would like to hand over to Renata in the lab. She will tell you a lot about how to properly handle samples. So see you a little bit later.
Hello and welcome to our preparation lab here in Karlsruhe. My name is Renata Janic. I'm working as an application scientist here, and I would like to show you today how to handle liquid samples, how to handle more challenging and complex samples, which could be liquid or pastas. So therefore, let's start with some sample preparation. For today, I prepared different kind of liquid samples and also different kind of complex samples, inhomogeneous samples. The easiest way to analyze liquid samples, for example, I do have here some samples like a solid homogeneous solution, like precursor or galvanic solutions, or maybe if you do have some mineral oil samples, here I have a biodiesel sample or some water-based samples. So the easiest way is just to take a volume, 5 to 7 grams or milliliters of sample, and to put it into the liquid cup. So this is just a cup stringed with a foil. Put the sample inside, close the lid, and that's it. And then you can start the measurement. Very easy and very common, but how to handle more complex samples? For example, if we have samples like these kind of sludges, slurries, you see you have particles inside. These samples are very inhomogeneous. They can have also very complex matrices, different matrices. There can be particles inside, smaller particles, bigger particles. So how to handle these kind of samples? Of course, these samples can also be filled into a liquid cup. So this is the easiest way. If you just want to have a quick overview of the sample composition, you can just put it into the liquid cup and start a measurement. These kind of samples, if the sample is inhomogeneous, if you have particles inside, of course, this will affect also the results of your analysis. There are a few ways to improve for. The easiest way is to take maybe this kind of sample and to dry it. Yeah? So you will get powder, which is of course also inhomogeneous. I prepared a few powders here. Here we do have some secondary fuels materials like waste material, plastic waste. You can also have maybe some wooden particles inside. Here I do have some material which is some rooftop materials. So you can cut the samples, or if you dry the sludge and slurries, you will have a powder, which can also be analyzed as a powder in the liquid cap. So first of all, this will also improve a little bit more maybe the matrix effect. You do not have to define, let's say, complex matrix in the software. So this is one way. On the other side, you can use the same powder. You can also prepare a press pellet. This is also very common. So this kind of materials can easily be mixed with some wax. You can prepare a press pellet and you will get a very nice stable sample that can be analyzed also very quickly. The next step, if you really want to improve the results for main compounds, you can also make ash out of these samples and mix it with some flux and prepare a fuse bead. So this is much more time consuming, but this is also a possibility to get best results for the main compounds. We can also have some kind of paste samples, more creamy samples. Sludges can be very different also in composition. Here I have some materials. For example, this is the palm oil sample, which is solid at room temperature, or also some kind of grease sample, which is a little bit smoother. This can also be put into the liquid cup, which is sometimes not very nice from the handling. Sometimes it's also not possible really to make it flat into the liquid cup. So this kind of samples could also be heated up on a heating plate and solidify the sample and just put it and pour it into the liquid cup. So this is one solution. For sludges, maybe this is not always the best way. So in this case, you can also use some kind of grease cups, yeah, so that you can buy them ready to use. So this is how they look like. You can put in very easily a greasy sample or let's say more solid sample into these cups, and then it's very easy to put it directly into a liquid cup like here, or if you have a smaller cup, these cups are also available in different diameter. You can also put it into this cup. Yeah. So this is also a very easy way to work with more greasy or more solid samples. What is important? There are a few tips and tricks. I would also give you some more information to this. So if we work with the foils for the liquid cups. So as you can see here, the liquid cup is trimmed with a foil. So different foils are available. You can have these foils which are already put on a tray. So this is a very easy way to prepare the samples. So this is the one I really like the most. Yes, they are a little bit more expensive. Then you can also have these pre-cutted foils. So they are already pre-cutted, so you have to remove it from this tray and then prepare the sample. So sometimes, depending on how thin the foil is, it needs a little bit of training and handling to prepare these kind of cups. And of course, maybe most of you also knows these kind of rolls which can be used. They are lower in price, but sometimes you also need more material, as this is a very thin foil, so you see it's very static. So this can also be sometimes a little bit challenging to prepare the cups, or you can buy ready-to-use cups. What is also important, you have to think about the chemical resistance of the foil, especially if you have some acid samples or maybe some gasoline-based samples. So then you have to use different kind of foils. You can test it easily if you pour the sample into the cup. You just keep it on a tissue for a few minutes. If you do not see any leakage on the tissue, you can use it. But anyhow, you can also inform yourself on the homepages of the suppliers. Typically, they have a quite nice overview of the foils and the chemical resistance, or which foil can be used. There are different thicknesses available. It's always good to have a thickness which is also good to prepare, but also a thickness which is not absorbing too much light element intensity. So this is about the foils. Also, the measurement time has to be taken into account. So working with liquid samples in a liquid cup, so the foil is also stressed while the measurement is running. So this is also something we have to take care that the measurement time is not too long. So typically, with a big floor standing system of 4 kilowatt, I do not extend 20-25 minutes of measurement time. So this should be the maximum. On the other side, you also have to take care of the sample itself, especially if you have these kind of inhomogeneous samples. If you have particles inside, it can happen that you also will have two kind of phases, like shown here with this used cooking oil sample. So you can clearly see there are two phases. So this means you also have to make sure that you homogenize your sample and that you quickly prepare the sample, that you do not keep them on the desk for a few minutes. So just prepare it quickly, homogenize it, put into the system. And also the measurement time. So if you have particles settling down while the measurement is running, this will mainly affect light elements like sulfur, chlorine. For heavier elements like hazardous elements like lead or mercury, this is not so critical. They are less sensitive to sample preparation, but especially for lighter elements, you will see an increase or decrease on intensity. So therefore, also the measurement time has to speed up a little bit. So this is also something you have to take into account. If you do not know exactly how to prepare, so you are also free, of course, to contact our application team, our global application team. So according to your region, you can reach out different application scientists. So we are also supporting our customer with tricks about sample preparation, especially if you have some more complex or inhomogeneous samples. Thanks a lot, and let's go back to the studio.
Thank you very much, Renata, for showing us some tips and tricks about sample preparation. Now we're here back in the studio for the second part of today's online webinar session. And here we will now talk about process and quality control of liquids and slurries.
Yeah, let's start with the first example. We look at cathode active material, the production of batteries. And typically there are different ways to produce nickel, manganese, cobalt, lithium batteries. And XRF is widely used because we can analyze the purity and the stoichiometry of the precursors, the dried hydroxide or the calcinated cathode active materials. And of course it's very important to keep a constant ratio between those ingredients and to know the purity of those chemicals. First of all, it's very simple to do a straightforward calibration because those are pure chemicals. So we can create the calibration solutions using nickel, manganese and cobalt sulfates. We calibrated our benchtop energy dispersive instrument S2 Puma. And actually we are analyzing the liquids under air because for those elements we don't have any significant absorption. We can use a pipette 5 milliliter and have a pretty short analyzing time, and using, for example, an XY autochanger system. The nice thing here is actually we can do a pretty fast, control of the incoming chemicals. Whenever you are doing process or quality control, it's not only about accuracy to have the appropriate concentration value, but it's also about precision. And whenever you are doing over time a control, you want to see small changes. And this is what you can see here, the nickel molar ratio and the deviation 3 sigma over time. And this, is outstanding. So this excellent precision enables a very close monitoring of the production process. And the second thing might not seem to be very tricky in the beginning. Whenever you are processing rapeseed oil, edible oils, one of the important steps is the phosphorus and calcium analyzed before the degumming process. And when you analyze those oil samples, you would recognize that the phosphorus values are randomly distributed, and because of separation of phases and unrefined samples are very tricky to analyze. There's one simple way: you heat up the sample and you steer it, and then actually you take the warm sample directly and analyze it. And by doing this, you ensure that you have always the same sample conditions and avoid the separation of phases or particles, right? Here we are using the S2 Polar since we want to look at lower ppm level. That's a pretty small instrument. It has a specific optic which enhances phosphorus and sulfur and have their better detection limit, and it's a pretty low cost of ownership. And with its inbuilt touchscreen, it's simple to operate for process workers. And here we see the calibration curve. We have a real phosphorus sample. You see here the spectra of samples overlaid, and you see the palm oil. You can really nicely differentiate between 11, 15, 19, or even 48 ppm phosphorus. So that's a pretty fast application here for this instrument. Yeah. When we compare, and that's the most obvious benefit of using XRF for edible oils here, palm oils, actually we have a result within 3 minutes. When we take the reference method, like using the colorimetric determination using the blue molybdenum complex, we would have a time of about 4 hours per sample. And here we actually get deliveries. We have 3 minutes, and then we can say that's the palm oil is ready to go into the processing, and we can pay the company who has delivered this crude oil.
Yeah, so we are really switching from something that is, sort of process monitoring in a not very fine-grained way to something that is really at spot, at line, production monitoring with this tool.
Mm-hmm.
Yeah. Now we've shown some example in the process and production control which have used calibrated solutions. So calibrations are always a good solution if you're dealing in a process environment with something that is always quite similar, so you can calibrate easily. You're looking maybe at some smaller variations of concentrations. You create some secondary references and you're good to go. However, in some cases you don't have samples or to calibrate, standards to calibrate. Or in other cases you may not need very high accuracy. And this is when our standardless solutions comes into play. So this is called SmartQuant. It works with full fundamental parameter mode. So essentially it means that we model the entire spectrum based on knowing very well what we have. So we know the geometry, we know the geometry in our system, we know how the different components interact, how the interference with the sample is, and this allows us to make a quite robust quantitative, semi-quantitative assessment of the sample without knowing anything about the material. So this is a quite unique solution, especially for raw material identification or also for all those various applications that we will talk a little bit in the second part with unknown materials from recycling and waste. I want to show a few examples where this can be used for more on the production side. Here more in the pharmaceutical and personal care products. Just an example here from where I'm comparing shampoo to hand lotion to hand gel. We can see different responses. So the shampoo has much the highest sodium content, of course, referring to some active ingredients inside. And so this can be easily quantified with SmartQuant. Here we see some of the results. So shampoo has about 0.3 weight% of sodium, whereas it has about 1.5 weight% of sulfur, just to give you an example here. And in this case, preparation is quite simple. You can simply pour those materials into a liquid cup and measure them as is. When you want to operate more precisely in personal care products, you would again calibrate, especially when it's about appropriate dosing of active ingredients. These active ingredients in sunscreen, for example, can be titanium and zinc oxide. So you want to use them just as much as needed because they can be relatively expensive additives in your material. And here you can measure the titanium and zinc concentration very precisely and accurately with XRF, shown here for energy dispersive system. Of course, when you want to go even more precisely, and accurately you go to a larger device. Again, like we've emphasized at the beginning, you calibrate it once and you're ready to go for your process and quality control. Last example here is toothpaste. So in toothpaste, we know that we have different levels of fluorine inside. This is a very important active ingredient in toothpaste, protecting our teeth over the time. And there are different levels of concentrations in the different products, typically a bit lower concentrations for infants and kids, and then higher concentrations for adults or very specific fluoride-rich geles. And fluorine is a very light element, so there's not much penetration into the sample, not much, the information depth is very, very thin, just on the micrometer or even sub-micrometer level. And here you have to take care about the sample preparation a bit more. So one option is here to use a little cup and smear it inside and then dry it and then flip it upside down and measure the material. This is what we've done here. Again, on an energy dispersive system, and with the high-sense XP detector, we really get low detection limits even for fluorine in toothpaste. And now we want to switch to some more complex examples. So when we're dealing with samples from waste and environmental samples or recycling samples. So here the applications and the materials can be manifold, and oftentimes reference materials are scarce. So SmartQuant, for example, is often a great solution. This can be the case for residuals from chemical processing or pharmaceutical processing, where we're looking into catalyst recoveries. It can be materials where we monitor like sewage and sediments or contaminated soils. And we are also looking into some regulated environments with XRF. You can see some numbers there on the right-hand side from Kai. So these are examples for concentration levels in sewage sludges. These sewage sludges, which come from industrial wastewater or also municipal wastewater or domestic wastewater, here can sometimes be reused in agricultural environments. And to determine whether it's usable or not, you need to measure the heavy elements, you need to make sure that there's not too much lead or cadmium or so inside.
Yeah, means the basic difference in this application compared to the first ones, actually, this is, you are dealing with surprise packages, means getting soil or getting waste somewhere. There could always be something in what you don't expect. And that's quite different to the application before. So actually we need to be aware that we need to monitor a large number of elements.
Yeah, but you need to always decide, can you use it for this application or not, or is it too toxic, for example? And in terms of the preparation, again, it depends a bit on your application needs. Oftentimes it can be quite sufficient to simply load it into a liquid cup. But in most cases, in terms of when you talk about sludges, industrial wastewater, recycling, you would dry the material, you would grind it and press it into a pellet before measurement. In rare cases, you might also fuse it for better precision accuracy for the majors and minor elements.
Yeah, so in first example, which can be a surprise package in terms of concentration, or metals which might contaminate it, the recycling of batteries from electric vehicles or solar panel storage means actually we separate the components and mill down the anodes, and so then we have manganese, cobalt and nickel oxide contaminated with lithium oxide. There could be iron, phosphorus in, maybe some carbon or aluminium and copper from the electrodes, from the packaging, fluorine from the electrodes. So actually this ends up in this so-called black mass. And we need to understand for value determination, but also for the recycling process, the ratio of the elements. And so we typically use this as loose powder. Whenever fluorine is one of the important parameters for recycling, we would need to go to pressed pellet. For the process monitoring, it would be much better to go for pressed pellet. Means milling, grinding is important, sometimes not easy when we look at metal parts which might be in. Moisture can be a topic depending how long was the storage. But we would use Smart Quant FP because it's medium range elements, and you can start with the S2 Ranger, with the S2 Puma, with the S6 Jaguar or the S8 Tiger, and you will get great results. Yeah, here you see that we have some samples measured. The nickel, the manganese, the cobalt, some traces like aluminium, tungsten, zirconium, and then we look at the ratios there, and we see, okay, we can identify the NMC type and actually go forward with on the one end, with the refunding of the people who are bringing this material back into our factory, but also with the processing. Now we are going into a field which is a little bit more different, because this can be sometimes really a surprise package. It is processing of waste. Here in this case, for example, the cement industry is using any kind of waste to replace primary fuels. It can be wood chips, it can be tires, it can be plastic waste. And this is burned, and of course we need to monitor the elements. On the one hand, the elements which are ending up in the cement, and like chromium, that's regulated. We don't want to have this. Aluminium, phosphorus can change the setting behavior. And of course there are some toxic element like cadmium. Imagine there is steel wires in these tires. They are zinc coated, and there's always a little bit of cadmium inside. So we need to monitor the cadmium for environmental reasons. And this can be really a surprise package. One day this can be okay. The other day suddenly, it's out of spec. You can go, on the one end, if this fits, you can go into a liquid cup here shown with wood chips. When you want to grind those soft materials, a freezer mill helps, a cryogenic mill, or using a normal mill and liquid nitrogen. This makes the material brittle, and then you can easily grind it and fill it into a polymer cup. The other method, of course, is take the powder, like shown here. It's carbon-based, use binder, and then form a stable pressed pellet. And those two ways are typically going hand in hand. In this case, we use an S8 Tiger Series 3, our latest model. It works with up to 4 kilowatt excitation. You remember the beginning of the presentation, it uses the advanced wavelength dispersive optic just to provide better resolution. This helps. And in most cement plants or in power plants, this kind of instrument is available. They typically are 24-hour operation. They have a fast sample throughput, very powerful for major elements, but also for traces. This new instrument, two features I want to mention. Whenever you are processing waste and you have a surprise package, you typically deal with huge concentration ranges. And typically detectors are suitable for a single narrow range, and then they will lose their linearity. And that's not the case, because we invented the signal processing software Sensor Boost. This eliminates detector artifacts and actually doubles the linear range of the detector. And this helps with surprise packages like aluminium. If I suddenly get waste with aluminium cans inside, this can be suddenly in the percentage range. The second thing, especially for traces like cadmium around the tube lines, we have the theoretical background model. It's also a patent. Here we calculate the background position, and actually this helps to get better net intensities and helps with the accuracy and reduces the required measurement times, because in most cases we don't need any background measurement. The question now comes into place, how do I calibrate? Because I cannot buy waste standards. And I need to monitor here, in this case, more than 30 elements. I want to analyze sulfur and lead in automotive fuels. Then there would be elements which are forming ash. There would be toxic elements. And we have a solution package called PetroQuant. That's pre-factory calibrated. And the good thing, it uses the fundamental parameter method, so we can deal with wide concentration ranges. It has an automatic selection of the best analytical conditions depending on these individual sample. So if you're analyzing low sulfur or low chlorine, or in the case of, for example, PVC, suddenly you have high chlorine, there are different measurement conditions. We can automatically quantify light matrix like the oxygen, and we can correct for different weights, for different sample shapes. And the nice thing when you put this instrument into a cement plant, actually you have clinker samples, you have raw meal samples, you have cement samples, and you can define the loader that it's able to handle the different sample types in different areas, so that the routine operation becomes easy. The camera in the grabber actually works with AI and automatically recognizes samples, so it will know exactly that's a liquid sample, vacuum mode is not allowed. Or it can read barcodes automatically, and you get rid of mixing up samples by typing in a wrong ID. One of the things I wanted to show, that's used oil, actually, the screening of waste oil. And we have here the ash forming elements, and then we have some heavy elements like molybdenum, additive, or copper. And actually you can see, independent of the weight, and the software calculates the right value. Just for cadmium, it gets a little bit weaker. The reason is quite simple. For cadmium, the sample must have been 15 centimeters thick, which is not suitable with the instrument. So there's still, the level is okay. It passes the test and will show you if cadmium is present or not. But the variation is slightly higher than with other elements.
Yeah, thank you, Kai. And with this, we would like to switch back to Renata, who will now show us the SA Tiger Series 3. And then after Renata's session, we will see you back here in the studio for the Q&A session. Yeah.
Hello and welcome back to our application lab. I'm standing here next to the new SA Tiger Series 3, and I would like to introduce you a little bit more of the system, especially what is important if we talk about the loading and handling of liquid samples. So let's have a closer look. On the SA Tiger 3, we have a new loader concept. So we have a grabber with an integrated AI camera. The camera is detecting the type of sample and also the cup which is loaded. In general, the loader is very flexible. You can have the so-called easy loader cups, which is this one here. So you can easily put a sample in. And for more complex samples, high samples, or a little bit more different in shape, you can also have the two-part cups, which are a little bit more flexible. You can have different areas defined by the user, and the software and the IA-based camera will always check if the right sample is loaded with the right cup, which is required by the method. I have already loaded some of the samples, which I have already shown you in the lab before. So here we have a few of the liquid samples just filled into the liquid cup. But you can also load, of course, the powder sample. So this is the waste powder sample I have shown you before, and the same sample prepared as a pressed pellet. So you can easily put them into the loader and start the measurement. What is important for liquid cups, of course, you have to run the liquid samples under helium. We have two different helium modes. Reduced helium mode to save helium and to reduce the costs for mineral oil samples or organic samples, powders. And we also have an atmospheric helium mode, which is only used if you have some volatile samples, for example, like gasoline. Measurement time is something I have told you, but I will give you some more information about this later on. And of course, it's not possible to run a liquid sample under vacuum, of course. And this is avoided by the AI-based camera into the grabber. So the grabber or the camera will detect that a liquid cup is loaded and automatically the vacuum is forbidden. So it's no chance that by any false use of the software, the user can load a vacuum sample, vacuum measurement for a liquid sample. What is also important if we talk about methods? So when we analyze materials like already shown before, sludge, slurries, maybe some more inhomogeneous samples, inhomogeneous powders. So this means the sample itself is already having a little bit higher errors due to sample preparation. So, but to get a good overview of the sample itself, you can easily use the so-called standardless method, SmartQuant WD, for the SA Tiger 3. So this is a ready-to-use method to really analyze samples from sodium to uranium, different materials. You can use different modes for solid samples, for liquid samples. This is a really good tool to analyze such kind of samples. If you're interested really to have lowest detection limits, for example, like very low chlorine or heavy elements or really hazardous elements like arsenic or lead. So maybe you have to improve a little bit the measurement parameters. In this case, you can set up calibrations, but quite often for these kind of materials, you do not have proper standards that you can use to set up your calibrations. So for this kind of material or requirements, we offer the PetroQuant solution, which is a ready-to-use solution already pre-installed to really analyze over 30 elements in liquid samples, powder samples, organic materials, or petrochemical materials. So this means optimized parameters for very low detection limits, also for hazardous elements, or, for example, low sulfur or low chlorine. So therefore, you can have different methods that can be used. Both methods are, of course, usable for liquids, and they do not exceed 20 minutes measurement time to make sure that the foil is not stressed too much by the radiation. With a new loader, we also have the possibility to really define, for example, areas where only liquid samples are started. You can also have areas, for example, where only solid samples are started. You can decide if you want to use a cup or for solid samples, pellets, or maybe also polymer cups, sticks. You can also use the grabber. So there's also the possibility to have a sucker included into the magnetic grabber, and then automatically the software will decide which grabber to use depending if you have loaded a cup or not. Very flexible, very fail-safe, and there's also the possibility to configure automatic positions. If you have daily routine samples or check samples, you can schedule them automatically. They are started by the software. Or for very urgent samples, you can also define in any position of the loader some automatic positions. So this means as soon as a sample is loaded into position, the camera will detect that the sample is loaded, and then automatically the measurement is started, which was defined by the customer. I will just show this by closing the lid. So now the camera will check the automatic position, which was defined in front of the tray, and as soon as the sample is loaded, it will start automatically. In this case, no sample is loaded, and so no measurement is started. Thanks a lot, and let's go back to the studio.
Yeah, thank you very much, Renata, for showing us the SA Tiger Series 3. We are now here back in the studio for the last part, our Q&A session. Mm-hmm. And we received a lot of questions during the session. So we will choose some of them now. So here's one. So we find in our material from time to time some particles, like metal particles, and we need to know where they come from. Is it possible with XRF?
Yeah, I take this question. It means you can do it in different ways. The one thing is you are using a small mask and actually just illuminate and place the sample on the mask and just illuminate the area. So you will get an idea, okay, that's the elemental distribution, and so you get ideas about the elemental concentration, what kind of material this could be. Or you take the small particles and use a liquid cup and place them on top of the foil. You can fix them with this sticky tape. And actually for metal, for example, would be easy to differentiate between different tool steel, stainless steel, iron, or if this is ceramics, from a surface furnace lining, for example.
Thank you, Kai. Another question is, we are operating a copper mine and we're looking into drill cuttings. How would we prepare these samples, and which device do we need for this application?
Yeah, and I've seen a lot of customers who are simply using liquid cups. Actually, you can use a handheld instrument, of course, a handheld XRF from Bruker, for example, or you can use a liquid cup and actually place the drill cuttings directly in the liquid cup, and typically the results are good enough, right?
Yeah. Can we also measure material from additive manufacturing, and how would we calibrate for such a application?
Yeah, here we are talking typically about metal powders, and they are quite similar like the battery cathode active materials. So you simply use a liquid cup, you place the metal powder inside, and you can use standardless software already, which are giving good results, especially for normal or for medium and heavy elements. One of the things, pressing for round-shaped metal powders could be a little bit difficult because sometimes they are not so sticky, right? So there, even the liquid cup method can be much more safer.
And maybe one last question for the Q&A session. What about the oxygen contents? We are measuring crude oil, used oils. How can we handle this, and how do we get good results?
Yeah, means you would recognize when you make a fresh oil calibration and everything looks fine, and then you are using a used engine oil or a crude oil. Actually, you would look, and if you have a second method, you would see that there is a deviation. And the reason is simply that, for example, for used engine oils, the oil is oxidized. So we have now suddenly oxygen content. And this actually, via the secondary matrix effects, actually will cause a difference in intensity. The PetroQuant software, or generally our software, is able to quantify this. So if you prepare the oil sample, and we know we analyze 100% of the sample, the rest to 100 is the CH2, and actually the Compton ratio, the tube Compton lines, the ratio, this is the indicator for the third element, which could be the nitrogen or oxygen. So we call it automatic because the oxygen concentration is already taken automatically into account.
Yeah, thank you very much, Kai. And with this, I would like to close today's session. I hope you enjoyed it, and I look forward to see you soon online again. Afterwards, we will send you the recording and also the slides. Thank you very much from my side.
Yeah, and also thank you for participating from my side. I really enjoyed it to do this seminar today again with Adrian. And I was really surprised to see your questions. I'm looking forward for the next webinar. Thanks.